All right, chemistry students, we're going to continue with chapter 7. Last video talked about types of energy, endothermic, exothermic, and defined this new term called enthalpy. This video, we're going to focus in on entropy, and then those two components will combine with temperature, looking at Gibbs free energy, or G for short. So that's ultimately where we're going. So we had ended on slide 16. Let's make sure this is okay. We had ended here. We're going to look at entropy first, and then we'll look at free energy. Okay? So entropy is abbreviated with just S, and it's different from enthalpy as an energy in its units. So you definitely want to pay attention to the units. But entropy is looking really at the disorder of a system or a chemical reaction. And we will eventually look at whether a process is spontaneous or not. So it's defined here, a process or reaction that once it's started, it's going to proceed on its own without any external influence, no added energy, no added pressure, no added temperature, nothing will force it, it'll continue on its own. So an example would be if you have solid ice, just like ice cube of water, sitting at room temperature, it will spontaneously melt. It'll change from solid to liquid. Okay, so what does that actually look like for entropy, okay, in the disorder? So several different things will look into entropy. One, we can just look at the phase of a substance. If something is a solid, you should know that those are the atoms that are really tightly packed together. They do vibrate a little bit, but not as much, whereas liquid, they're more spread apart, take the shape. Liquids take the shape of their container, and then gases are even farther spread apart, and they take the shape and the volume of their container, okay? So as a substance changes from solid to liquid, the entropy value increases, as well as if a substance changes from a liquid to a gas, the entropy value increases. Another component, if you're thinking of entropy of a reaction, is fewer moles to more moles. That direction, entropy would increase. This diagram shows entropy decreasing as we go to the left. Okay, so you think of it kind of like if cards were moles, we've got one pile of cards, 1 mole, and then over here, entropy would increase as you sort of change and shuffle or throw all the cards around, and you have individual cards. That would be more moles. Okay, so I have a list on the next slide of examples of where you would see entropy and apply entropy changes that would increase entropy. So we'll just focus on increase. And obviously the opposite would be a decrease in entropy. Okay, so a reaction whose products are in a more random state. That was like the cards, or even the solid to liquid to gas. Gases have more randomness, and therefore they have higher entropy, or S, higher S, okay? Reactions that have larger number of products, okay? So if I have reactant A, B, and they separate out into A plus B, this is 2 separate products, and therefore this reaction increases in entropy, AB separating out into A plus B. An increase in temperature will also increase the entropy. There's a temperature component you can see later on that, remember, the unit for entropy is joules per K Kelvin, okay? And so an increase in temperature will increase the entropy. Usually, as you'll see as we move on, that is because the molecules move faster, more collisions, greater disorder overall. A solid dissociating into ions upon dissolving into a solution, that is also an increase in entropy. And your book has an image of that. Salt dissolving in water. Okay, so you can sort of see the water in the beaker here, and then the pile of salt at the bottom. So this would be the solid salt, all ordered, cations, anions. And then this would be all the red and white, or the water molecules surrounding the appropriate ions that have separated into solution. And as you see, as we go from bottom to the top image, we have an increase in entropy because separate ions are more disordered than the collective solid at the bottom of the beaker, okay? Another example here, you could think of ice in water. Heat does have to flow from the water to the ice for S to increase. And that will occur because the liquid water will be warmer than the ice water, and therefore you would have an increase in entropy. So these are all examples. You're thinking in terms of disorder, you're thinking in terms of more randomness, all of that for increase in entropy. Okay, just like in enthalpy, delta H was change in enthalpy, delta S is change in entropy. Okay, so if we have an increase in disorder, delta S is going to be positive, and we decrease, that would be like going from liquid back to solid, decrease in disorder, then the delta S is going to be negative in a chemical reaction. Okay, reactions are going to be spontaneous in the direction of lower chemical potential energy. Okay, here's an example of graphite. Interestingly, graphite, that's like your boring, ugly image here on the lower right. Graphite is more stable than diamond, although both of them are made of carbon. It is spontaneous for diamond to change into graphite. And up here on the upper part of the image, they're showing kind of like a crystal structure or a lattice format of the entire, all of the carbon elements of the entire either graphite or diamond structure. And interestingly, the graphite is a more stable form than the diamond form. So it is more stable to be graphite. However, the process is really, really slow. So if you have like a ring with a diamond in it, it's not going to turn into pencil lead in your lifetime or even several generations. It's a very, very slow process. But technically, it is more stable and spontaneous to occur as graphite than as diamond. Okay, so that's entropy. Your homework's going to have some questions about entropy and things like that. What looks like entropy? Is this higher entropy or is this decrease in entropy? That kind of thing. Okay. So as a recap, enthalpy, you're looking at kind of heat of a system, and that unit was in joules per mole. Whereas entropy, you've got that Kelvin added in. Okay, that Kelvin unit. So this K is not kilo, it's Kelvin. Remember, it all comes back to energy. We want to know energy of a reaction. Okay? Chemists want to know if a reaction is spontaneous or not. Is this going to occur on its own, or do I need to add some extra component to get the reaction to actually take place? A negative delta H favors a spontaneous reaction, and in general, a positive delta S favors a spontaneous reaction. Ultimately, we're going to combine both of them with temperature. Both of them need to be considered with the temperature to determine if a reaction is actually spontaneous or not. Because if you have a really high temperature or low temperature, we may or may not have a spontaneous reaction. Okay? So that brings us to Gibbs free energy. Gibbs free energy. You must know this equation. Put a star, highlight, memorize, flashcards, this equation. So the Gibbs free energy, or just free energy change for short, is a measure of the change of free energy, the whole reaction, okay, that takes place. The units are often in kilojoules per mole or joules per mole. If you notice, delta G, the free energy change, is equal to that enthalpy minus temperature times entropy, okay? I just want to make a note of the units here. If this is kilojoules per mole, that would make sense, because this is often seen, enthalpy as kilojoules per mole, minus, and if I have temperature, which must be in Kelvin, do you see that? So temperature is in Kelvin, and I'll put a big parenthesis here, and then a little parenthesis, Kelvin times whatever our entropy is, and that was Kelvin on the bottom, kilojoules per mole or joules per mole. Okay, do keep in mind, if you're asked to find Gibbs free energy or this free energy in kilojoules, every component, enthalpy and entropy, has to be in kilojoules. You may be provided with, say, entropy in joules per mole Kelvin, and therefore you need to convert it into kilojoules before you use this equation. But if you see, the kelvins would cancel, and then our final units would just be kilojoules per mole if there were actual numbers in here. Okay, so let's look at this equation and look at just what is spontaneous or not for delta G, and then we'll do a little bit more analysis on spontaneous or not. Okay, So that's the equation you must know, okay? If delta G is negative, the reaction is spontaneous. So let me list this out for you. Delta G is less than 0, we call that a spontaneous reaction. So we write out a reaction whenever A plus B goes to C, and I told you that delta G for that was negative 10 kilojoules per mole. That would be a spontaneous reaction. You would just know by looking at the fact that that number is negative. That 10 is a negative 10. If delta G is greater than 0, that's not spontaneous. Now you may hear in some classes or in some cases, instead of the word spontaneous, they use the word exergonic. And instead of the word non-spontaneous, they use the word endergonic. Those are just synonyms for the spontaneous or non-spontaneous. If you were given individual G of products or reactants, you could calculate delta G with the same kind of, final minus initial, products minus reactants as you've seen before. Okay, with like change in temperature, it was final minus initial, products minus reactants. Okay. What happens if delta G equals 0? Well, that reaction is going to be at equilibrium, which is the next video. It's a later part of chapter 7. Okay, so if delta G is exactly 0, then that chemical reaction is at equilibrium. Like I said, we'll look into that later. I want to recap something because we did enthalpy in the last video and we just looked at entropy. Since all these values are on here, these two blue ones you really need to know. Okay, I just want to recap. When delta H is negative, you have an exothermic reaction and heat will be released. When delta H is positive, endothermic, heat is absorbed. Okay. Remember we compared heat and temperature in the first video. Okay, so before we continue, I want to go over something because what oftentimes chemists want to know is a reaction spontaneous at all temperatures, high temperatures, low temperatures, that kind of thing. So if we have this reaction, in general, we're just going to look at positive and negative enthalpy and entropy. So we're going to have several categories. I'm just going to put spont for spontaneous. Spontaneous at all temps. Okay? And then we're going to have another category. Spontaneous in reverse. That would be as a going from products back to reactants at all temps. In other words, maybe something that's not a spontaneous reaction normally. And then this next category, spontaneous above a certain temp. Okay, these are all related to temperature. And then spontaneous below a certain temp. Okay? Ultimately, you could solve what I'm about to put in for you in a table using, say, +1 or -1 in this reaction for all of the values of H and S, okay? So in general, if delta H is negative and delta S is positive, you plug in a negative number here, positive number here, you're going to get a really always negative delta G, and therefore spontaneous at all temperatures. The opposite is true in the second column. If delta H is positive and delta S is negative, generally you're going to have a non-spontaneous reaction, and that's why this label is spontaneous. In the reverse at all temperatures. Above certain temperatures, if delta H is positive and delta S is positive, you could have a spontaneous reaction, but that's going to be if temperature is really big. The subtraction of this value on the right here from enthalpy will allow you to have a spontaneous delta G, okay? And then below a certain temperature, if delta H is negative and delta S is negative, then you will have a spontaneous reaction. So it would basically be if T is kind of small, all right? If T is kind of small. So being able to analyze that and understand that is really important, because that's what chemists are going to do. You would be given actual values, or maybe you'd have to calculate delta G, and then you'd get a negative value and you'd know it was spontaneous. But analyzing this will really help you understand the Gibbs free energy equation and use the values of enthalpy and entropy easily. Okay? So we're going to move on to the next section, which is reaction coordinates. Okay? And reaction coordinates, so you know what it is, because we're not going to get to it for 2 slides, is basically a graph. So you're going to have a graph that's going to show you the progress of a reaction. So the x-axis is often called reaction. Sometimes it's called RxN for short. Sometimes I've actually seen it as time going that way, but ultimately as the reaction progresses on the x-axis from left to right, you're looking at energy on the y-axis, okay? And that energy is usually delta G energy. So it's going to be kilojoules per mole or joules per mole. Sometimes people just put plain Jane energy and they don't label it as G, okay? And what you're going to see is the reactants start at a certain energy, reactants, okay? And the products could end up at a higher energy, or they could end up at a lower energy. I'll just make them a lower energy, okay? So products as time progresses. Now, here's where students get confused. We will have some kind of barrier to overcome, some kind of energy barrier. We can't just connect reactant level to product level as one line, like dotted line here. There's going to be some energy of activation, so we kind of make like a swooping hill, make it a nice smooth hill, okay? And what you'll see is you can have sort of a couple shapes of that hill. You could have a shape where the reactants are high and the products are low, and this is like wee down the hill, okay? Or you could have a shape where the reactants are low. We still have to go over the hill and the products have a higher energy, okay? So let's actually go and look at a diagram in a couple slides, but that's the goal of the reaction coordinates. We are going to label some more stuff on a reaction coordinate. Just to be clear, three things do need to occur for a reaction to occur. We have to have collision of the reactants, the correct orientation, and the appropriate energy for the whole thing to take place. So this is showing you can form a bond between nitrogen and oxygen in this diagram. We have an intermediate that's probably a very high energy. That would be like the top of the hill on that reaction coordinate. And then we break up into the appropriate products, okay? If the orientation's wrong, like here where the oxygen is facing the other oxygen, then no bond can form, no collision, the collision is ineffective, and that doesn't occur, okay? So this is the image of a spontaneous, see, exergonic spontaneous reaction coordinate, okay? You should be able to draw this from memory, but there's the X and Y axes with the energy here on the Y axis and reaction going from left to right, okay? Two things that are on here that weren't labeled on my other graph were the distance between the level of reactants and the top of the hill. Okay, that distance is called the activation energy, which we abbreviate EACT, okay? The difference between reactants and products is the delta G of the reaction, okay? The overall delta G, that would be like A plus B produces AB, and delta G for that is negative 10 kilojoules per mole, okay? And that would be here. This would be about 10 kilojoules per mole difference here, okay? So this one here is showing a spontaneous reaction in its smaller version on the left of this slide. And here is the non-spontaneous or the endergonic reaction. We still have the same distance between reactants and the top of the hill is the activation energy, and the difference between products and the energy level of reactants is the delta G of the whole thing. But if you see, products have a higher energy at the end than reactants, okay? Activation energy, that EACT, okay, that EACT, do you see that EACT, it's really important, is not going to change the delta G of the overall reaction, okay? That activation energy is like, how do we get to the top of the hill? Because once you make it there, you can woo down the hill to the products, or in this case, woo down the hill to the products, okay? Something we're going to get into next is going to be reaction rates, okay? The measure of how quickly the reaction actually occurs. How well can we get over this hill, over the activation energy barrier, okay? So just to define it, reaction rate is the speed at which reactant is used up and product forms, okay? So you're thinking speeds kind of like physics class sometimes. So how fast can we get from reactants to products. Like the formation of graphite from diamond is pretty darn slow, so it's a very slow reaction rate, okay? You're thinking of the same thing we already talked about with the collisions, the orientation, the energy from a few slides ago, okay? But you're also thinking, how could I speed up reaction rate if I needed the reaction to occur? Well, you could increase the temperature. What does that do to actually increase the reaction rate? The molecules will move faster, and therefore you get more collisions, okay? So if you see, that's what this diagram from your book is showing. Increase in temperature leads to increase in frequency of collisions, as well as the force of those collisions, and therefore we get an increase in reaction rate. We haven't defined concentration in here, but you could think of it like the amount of, the amount of materials. It's an M here. The amount of materials in the reactants. Okay, if you dump in more reactants, okay, increase that concentration, then you're going to have more reactants to react, and therefore we're going to increase, sorry, I'm just trying to underline that, increase the reaction rate, okay? One thing, you're going to have a homework question where it's like, what's true about reaction rate, okay? The reaction rate is not, this is a true statement, is not determined by the value of delta G. So you could have a homework question that would have select the false statement, and if one of the statements says that the reaction rate is determined by delta G, that would be the false statement and the correct answer for that question, okay? We're going to add one more thing to our reaction coordinate, okay? So this is just the blue line here is the original reaction coordinate for the spontaneous reaction that we've already seen. Once again, x-axis is reaction, y-axis is free energy. But scientists will sometimes add a catalyst. In biology class, enzymes, this bottom bullet, are biological catalysts. That's really all over the TEAS test. There are questions about, are enzymes biological catalysts, true or false? Yes. What do they actually do? Well, if you see the red line I marked over the blue line has no catalyst present and a very high activation energy, very high peak to overcome. Whereas if you dump a catalyst in, and this green line does have a bit of a curve to it, we lower that hill. I'll even draw another one. We lower that activation energy. The catalyst does not change the delta G. It only lowers the activation energy for the overall reaction, okay? Really important. So the last thing I want to show you is just a table from your book that goes into reaction conditions that affect equilibrium, and sometimes they affect reaction rate. It's got the change, pressure, catalyst, temperature, concentration, and then the effect. So some of this may not make full sense if you're like, favors product, what? When we get into equilibrium, it will make a little bit more sense, but since this was all in the section under reaction rates, I want you to see this table now and keep referring back to it as we look into equilibrium, which is the last video for chapter 7. It's going to be equilibrium and Le Chatelier's principle. Okay, so these are the sections from the book, but you can end here for this video. Thank you for listening.